we have a bunch of practical courses on this stuff. Okay, like codes are technical documents. At the end of the day, they are essentially ways that say you will do this, you won't do that. These are the way we will measure all of these things. This course is actually a little bit of a step up from that. And I think it's important for most people because a code is just a document. Like I often used a joke when I still worked with Ulrich at the city. The minute you finish building a building, you can go burn your version of the Alberta Building Code. It's done its job. It is a design and construction manual. It's a useful one. It's a legal document. You have to meet it, but that's where its powers and authorities end. Today, we're going to talk a little bit more about the actual underlying structure for that stuff and how you apply it, because that, to me, answers the fundamental questions of why. Like, why do you do any of this stuff? Yes, the short answer is I do it because it's in the code, but when you get to a complicated building, following code stops working. I'll give you a good example. I just was talking with a former colleague of mine who's representing the city from the building safety perspective on the new arena. And he said it perfectly, which is there's no part of that building that the code really applies to. You have to make it up as you go along. And if you're going to, quote unquote, make it up as you go along, you better understand why all of those parts are in the code to begin with and what the implications of all of them are. It's the deeper understanding. It's why, I hate to say this and I don't want to get political on this, but it's the reason why politicians get to make laws, but you have a bunch of lawyers and judges whose job it is to actually write them and interpret them because they understand the deeper nuances of how you go through this to say, well, you intended this with your law, but I don't want a bunch of people falsely convicted or a bunch of guilty people going free because you didn't understand the details. In order to do that, so we're gonna talk about a few things today, and I kind of just call this NBC 9.36 workshop lifting ideas, and I guess it's a little play on words there, but the idea to me is figuring out what the background for a lot of this stuff is and how tiered codes can be used in a much more constructive way, because that is the interesting part to me. You know, I was joking with Juan before we started this morning. If you literally just said, how do tiered energy codes work? I can give you that lecture in 15 seconds. You must be better than the baseline by a certain amount, and the code will tell you how to measure that amount. Done. That is the start and end of that conversation. Now let's talk about where that comes from, why that means, and how we got to where we did is a little bit more nuanced, a little bit more interesting, I think. So we're going to talk about the legislative frameworks. We're certainly going to talk about the NBC sections that are appropriate, NECB where it comes in. We'll talk about that more tomorrow if you're coming back. And understanding the new tiered energy code requirements and understanding them, hopefully not just on a technical level, but on a little bit more of a philosophical level as well. We'll cover a bunch of stuff today. I'm not going to waste your time with this because we had a lot of slides to go through. I'll let you read this, but essentially with the Codes Accelerator Fund, so one of the things that has happened in Canada is the idea that we have said codes they've grown up is the only way I can phrase them. If 25 years ago, if you looked at codes, all they were life safety standards, full stop. Do this, don't do that, you'll have a safe building. It worked okay. However, codes have started addressing things like accessibility, durability, energy efficiency. Those are not life safety issues. They are quality of building issues. And that's a really important construct because people will talk about meeting code as though it's some kind of, moral obligation moral imperative that they've got. The other way to say you've met code is if I did a slightly worse job, it would be illegal. That's the actual legal definition of code. Code is the minimum acceptable standard you can do. So bragging that you've met code on a project is basically saying, I narrowly avoided being sued. That's a pretty low bar to set. And when you look at these things that talk about tiered energy codes, it talks about how to take codes as a base and say, can we use them as policy drivers? And that's a really interesting point to me because we've never done it before. Ulrich alluded to the climate commitments to the city of Calgary. We're not going to debate whether or not climate change is happening, what your belief system on that is. To me, that's irrelevant. What is important is we do have an emissions problem. And emissions can be anything. I think back to, if you ever want to humor yourself, go Google a photograph of Los Angeles in the early 70s. And the entire city is blanketed by a haze. And that haze was emissions from automobiles primarily, because there was no catalytic converters in those days. There was nothing. They were burning leaded gas. And all the things we talk about, whether it is energy efficiency for greenhouse gas emissions or energy efficiency for saving money or a cleaner environment, I don't care. They're all applicable. We just need a way to measure all of this. And I just wanted to share this with you because I know that the colors are inverted for the importance of today, but I just got to point something out, which is all of the gray stuff is intimately linked to the greenhouse gas emissions of the city of Calgary and buildings. So buildings account for about 2/3 of our greenhouse gas emissions in one way or another. So they are the problem. It's not that it's kind of like, you can't look at it and go, oh, the problem is the buses or the diesel. No, the problem is the buildings. And that's a meaningful thing to say, because it means if you identify the problem, well, what's the old adage? The first step in solving any problem is identifying what the problem is. The second thing I wanted to point out, and this is the wedges diagram that talks about the province, that says, how are we going to address greenhouse gas emissions overall? And I just want to point out, there's few things that are beyond our control. So I can't control the provincial grid. How NMAX makes electricity, whether it comes from a coal-fired plant, a natural gas plant, wind, nuclear, imports it from BC, I don't control that. They do. But what I do control, and the reason it's highlighted, is that red chunk. That's energy efficiency in buildings. And I didn't put it in this set, but if you look at the energy consumption per square meter for buildings in Canada, it effectively has been flat since 1920, which is a wild thing to say, because it means in a century of energy efficiency improvements, we haven't actually demonstrated real world energy drops in a century of trying. That's, if I put my cynic hat on, that's embarrassing as an industry. Like, imagine if we worked in aerospace and you said, yeah, we fly the same way we did in 1926. You would be laughed out of the room. People would look at you and go, that is ridiculous, because wooden canvas single-seaters is all we had then. I kind of like my 747s and all my important stuff. So if I was to summarize this in a nutshell, we have a large number of underperforming buildings, a greenhouse gas and image problem. The image problem is province-wide, and no comprehensive zero tools guidelines to fix this. That's a pretty big statement. And I guess I'll have to ask the question that says, is that actually true? And to me, one of the most important documents that came out in the last few years, and it's one that nobody talks about, but I got to reinforce it, was the City of Edmonton and City of Calgary they signed what was called the City Charters Act with the province. And the City Charters Act, so up until that was signed, every municipality was treated exactly the same by the province. It didn't matter if it was a municipality of 52 people or 1.5 million people. And somebody said, well, that isn't reasonable. And they're probably right. So what they did is the City of Edmonton, the City of Calgary, and the province sat down and said, what are some of the powers that we should be giving to a municipality to make sure they can do what they need to do in the bigger context of things? And one of the things that came out was this. So you can read these for yourselves, but basically the City Charters Act recognized that both major municipalities must have a plan for mitigating and adapting to climate change and the ability to write laws around that. So that's why you probably all heard that there was a City of Calgary Council declared a climate emergency, right? That's where that comes from. That's a recognition that says, I'm probably not too worried about vehicle emissions in a town of 150 people. I can't drive enough to make a problem out of it. There's 1 million cars in Calgary. I can actually make a very large problem for people with asthma if I don't have something that allows me to address that. Second one is you have to update this thing. So it's not a document that you write. So once you have your adaptation and mitigation plans, you are obligated to revise them every 5 years because things change. Technologies change, economics change, Politicians change, everything changes. The more important ones is when you look at the details of them, and I've given my little interpretation. One of the things that was clearly laid out in there is if I'm doing a development in the city of Calgary, as a planning authority, the city of Calgary can use environmental criteria to determine if that project should go ahead or not. That's a really big step, because it means I don't just have to meet use and zoning and building height now. Now I can say, wait a second, what is your impact on the environment? Is this an environmental reserve? Is it going to negatively impact my neighbors? What is it going to do for that? And to be very frank, it's what larger cities have been doing for a century. So we're kind of long overdue in having that legislation here. This one's interesting, and I keep this in here as a reminder that nothing is forever. So originally, when you read the City Charter Act, the cities of Calgary and the cities of Edmonton were effectively allowed to set their own tiers in the energy code. That power got revoked by the province. They said, no, the province wants to set this, the level of tiered compliance, you have to live with it. So we had an opportunity as a city to do whatever we wanted. We could have said we were a tier 3 city. We didn't act on it. And by the time they thought that it was a good idea to do something, the province came along and said, no, sorry, we're going to revoke that power from you. And that's why there's an important temporality to all of this, which is really talks about how you deal with these things in a framework, because that's what all buildings are. Every building, like any good architect will say this, a building is a reflection of its time, right? The reason we all go and see like big cathedrals in Europe is because not that we can't build them anymore, we won't. The days of having a 240-year project by master stonemasons for a church, it was wonderful. They're beautiful buildings. It ain't going to happen in my lifetime, and certainly not anymore. Like it's out of its context. Well, the same thing can happen in legislation. So, long story short, for the last half dozen years or so, we've had a couple things. We've had an obligation to create and update plans. We can use environmental considerations in approving development and development permits, and we may put in place incentives to encourage. And that's not a bad set of rules to follow if you're going to want to build better buildings. Now, how do you go build better buildings? That is a question that is often, everybody assumes you can just wish it into existence. I've been in some way, shape, or form involved in construction for over a quarter of a century. And from my experience, and maybe I've just had a lousy career, I'm not sure, but I have never seen anyone wish a building into existence. It hasn't happened. I haven't seen it. I don't think anyone I know has seen it. But they're large economic propositions that take a lot of skilled trades, a lot of design professionals, and an awful lot of money to do. So they don't come about by chance. They have ideas behind them. And ideas are important. So I want to abstract this a bit. And if we just humor me for a second, let's take a chart. So the vertical axis is number of projects built. And this is some measurement of sustainability. And call it energy efficiency for what we're talking about today. And you'd expect some form of distribution. You're going to have a few buildings that are really good performers. You're going to have a lot in the middle that are kind of, your code compliance things. You'll have a few that really failed at what they did. That's pretty much, I don't think that's a crazy or radical start for where we're going. But the question is, when you want to fix it, you have to realize something. If you're on the low end of the scale, you only respond to minimum standards. Giving somebody $5,000 for a better chiller on a warehouse that's being done to just, again, narrowly avoid prosecution, they're not changing their ways. You have to change the laws for that. You have to change the minimum standards. Conversely, this building is a good example. So this one, if I'm not mistaken, was certified under the LEED program. Every part of this building probably exceeded the code requirements. So changing code doesn't change this building one iota. What it responds to is things like incentives, market opportunities, all of those things. It talks about doing things for a very different set of reasons. Now, if I just rely on regulation, I'm going to only affect that bottom end of the spectrum. Changing the minimum code requirements doesn't help me here. Conversely, if I only offer incentives, I'm only going to be changing the top end of the spectrum. Guys at the bottom sit there. So if you want to actually move an industry, which is how things become affordable, because if on either end of the spectrum, I've got narrow groups of people doing the work and I can't get any effective scale, I can't get the products imported, I have to move an industry in order to make it sensible. You have to have some kind of push and pull, okay? So the pull is the incentive side, the push is the regulatory side. And if you can affect both of those, you will actually move an industry. Why am I talking about this? That's what a tier is. A tier is a way to use incentives and regulation to push an industry. And I'll go back to my aerospace analogy. That is exactly what happened in that industry. When Fokker Industries in Holland decided wooden canvas is good, but I'd really like to build a metal airplane, people thought he was nuts. Turns out he was onto something, because the minute you actually change the way you manufacture an airplane to adopt aluminum, yeah, we have wood airplanes still because we like quaint and home-built projects, but when you get on a 787, or that's a bad example because it's carbon, when you get on a Boeing 777 or an Airbus, what is it? It's 90% aluminum, because they've changed the industry. And what I would suggest is there's a very simple kind of way of looking at this, which is if I have a series of, whoops, it was on me. If I have a set of objectives that are set forth, and that's what that climate plan really does, and I can talk about a good set of incentives related to buildings that have a focus, I have my pull, and I can use energy codes and the tiers of energy codes as setting appropriate minimums, I'm going to get better buildings. And that's something this industry, as I said, has largely failed to do in a century. So that's my motivation for talking about any of this stuff today is exactly that. So let's look at some of this, because there's the realities of this, and I'm going to apologize. I am not a lawyer, and I don't know if anybody else finds the legalities of buildings at all interesting, but I will say, again, in my limited experience, the legalities of construction have as much of an impact on the project as anybody's design and anybody's craftsmanship, because they're expensive and people get sued in them an awful lot. And I do have to share this with you. Lawsuits in construction are very interesting because you can't point to a single point of failure. So you're driving down the road, your Ford car explodes. Do you sue Mazda? No. You sue Ford because they built the car. They're, at the end of the day, effectively responsible for every component of it. You own a building and your roof leaks. Do you sue the supplier who gave you the roofing membrane? Do you sue the installer? Do you sue the HVAC contractor because they left fasteners on the roof that people stepped on? Is it a failure at the time of construction, or is it a failure due to movement in the structure because the engineer never did the appropriate settling calculations and it tore the membrane? Long story is, nobody knows. It's rare in construction to walk up to a building and go, that's your problem. Bob did it. Like, that doesn't happen. So when you get sued in construction, everybody gets sued. That includes the city, that includes the contractor, it includes the developer, it certainly includes the trades. It's a very complicated legal structure. And the legal structure for our legislation is not a whole lot clearer, but let's see if we can't walk you through it just a bit today. So we have this pyramid, and this pyramid should read as a pyramid does. The base supports the one above, which supports the one above that. And the other way to look at projects, of course, and it's not perfect for all of Alberta, but it's close. But in Alberta, you have kind of a general three-part system to talk about things. You have an owner, you have a development permit, a DP, and you have a building permit. And if I was to be very blunt in how they're done, you have somebody who initiates a project and owns it and pays for it. You have a group of people who are looking at what the building is, how big is it, what is it used for, and you look at somebody at how it's constructed. The building permit effectively says, let's construct this thing according to what we should do. With respect to energy, the owner largely gets to set the goals. We'll talk about what that means in a second. Development permits set a lot of the context. So by the time you've filled out a DP, I know how big the building is, I know how tall it is, I know how much glazing it has. I've set the context. I've actually set about 35% of its energy consumption, to be honest. And then the energy efficiency metrics is built into the energy codes of how you do it. So that's what you are actually putting in there. What is the efficiency of the HVAC units? What is the R value of the wall? What is the U value of the window? What is the air leakage of that assembly? All of those things are built into that. Together, they actually provide the whole picture for energy efficiency. And I think we have to understand a couple things. Let's start with the base of this, which is a provincial authority, and understand two things. As I just covered in that city charter, it's unequivocally now the province sets the minimum standard. Okay? We're tier 1 province, but that's it. The province sets that level. However, 2 points that are often missed. An owner can do anything they want if it exceeds code. Again, think of it, a code as a floor. I have to hit the floor, but I can also be up here. An owner can choose to do that. It's completely their prerogative. Anything that exceeds code, they're more than welcome to do. Second part that is often forgotten is owners. When you read the Alberta Building Code, it is, again, crystal clear. Owners are responsible for building code compliance. Not consultants, not contractors, not cities. Owners. That's why those two statements are really interlinked. Because the owner is responsible for achieving the minimum standard, they can also set their own standard that's in excess of that. So, when I say they kind of set their own objectives, an owner can build to any standard they want provided it meets code, but it is absolutely voluntary. Why might you want to do that? Because weirdly enough, when you are selling a $500,000 object like a house to someone, there's a lot of points that go into that decision. It's not going to be, very few people drop $750,000 on something because it's blue. Okay, it's a much more complicated issue. The design, the location, the amenities. Well, one of the things that's been really interesting in the last few years is the growing importance of energy efficiency. So go look at don't take my word for it, take Jay Westman's for it. Just a very wealthy man, because he understood something several years ago. He could sell energy efficiency as a package to people. So Jamin does offer tier 1, 2, and 3, I believe it is, of energy efficiency packages to every home they sell. Because almost 2/3 of the people think there's a value in that. And they will give them money to do that work. The second thing is, legislatively, the public is actually in support of minimum energy efficiency legislation. And the reason being, I think, is twofold. Number one, people want to feel good about their purchase of a building, and they want to know it's constructed to a certain level of energy efficiency. Number two, directly impacts their utility bills. Like, there's an economics driver behind all of this too. And it's funny, like when we talk about gas bills on a house, yeah, it's a few $100. Go heat a warehouse one afternoon and see what their utility bills are, because all of a sudden now it's several $1,000s a month to heat a building, and that's a big number. You know, if you're ever leasing space, just again, I'll point it out. Don't take my word for it, but next time you just check out what the op costs for leasing warehouse or commercial space is, because it's going to be somewhere between $4 and $14 a square foot. That's a non-trivial number, guys. Like, that is a lot of money that's leaving your pocket. Right now, if I go downtown, because of the vacancy rates, I will pay more in op costs than I do for leasing commercial space. Op cost is basically utilities, the property. It's all the operational costs that the tenant pays for the owner of the building. But utilities are an enormous part of that. So it's not a non-trivial, it's not a non-zero number. Last thing, I always like this one, because when people are asked, hey, what's important to you? This is the list. This is done by the Canadian Home Builders Association. They do this every year. They basically run a survey that says what's important so we can help our builders build better homes and more sellable homes. Well, everything in red is directly tied to energy consumption. So almost half the list is some form of energy efficiency things. Why am I boring you with this? Because the economics to making a more energy efficient home are actually there now. It's not a huge capital cost increase. It is a sellable feature that has a value intrinsic to people, and it may give you a competitive advantage over the house next door. Those are all important things if you're building 500 tract homes a year. Now, with all of that said, as I mentioned, any kind of energy efficiency standard that's above the bare minimum is going to be voluntary. And how do you keep that in mind? And I just put a pin in that, because part of the reason we have papers on the desk is we're going to ask you to think about that in a while. But please just mentally put a note in that question of how do you help someone or encourage somebody to do above code. Speaking of codes, let's talk about the Safety Codes Act. The Safety Codes Act is probably the biggest one here. In short, the Safety Codes Act is a piece of legislation that makes a building code a law. Okay? That's really, if I was to just dumb it down, sets your minimum standards, gives you procedures, gives you a legislative framework for which you can enforce building codes. That's why when you are in industry, you will often hear the City of Calgary referred to as, and I quote, an authority having jurisdiction. That's the language that the Safety Codes Act uses to ensure that the City of Calgary gets to enforce building codes. Just a couple quick pieces of legislation, and again, I'm not going to pretend to be a lawyer, but I just want to say, so there's a relationship between NECB, which is the National Energy Code of Canada for buildings, which talks about large buildings, and 9.36, which talks about smaller buildings. But the one I want to talk about most important is actually this box up here. And that box is important for two reasons. You can read it at your leisure. I'll just fill in the background. So first thing I got to point out, it talks about a national building code and a national energy code. And it talks about both of those things without hierarchy. That means you are obligated to meet both of them at all times. That's important. That means the legislation is on an equivalent footing. So from the perspective of the government, whether you are dealing with life safety issues or whether you are dealing with energy efficiency issues, the legal framework is identical. It just lists the documents. It doesn't say, do this, and if you have time, do that, or do this instead of that. It doesn't say that at all. It says, here's two pieces of legislation. Go follow them. The second thing is I wanted to point out, it did establish what we have as a Tier 1 province. And again, that was part and parcel of that retraction of the city charter rules that said, nope, you don't get this side. The province is going to decide for you. Going on to this, the Safety Codes Act affects the last part of the typical process. It really talks about how you are going to do this stuff. And I'm of the opinion that there are a lot of ways you can measure building performance. Tiered codes just happens to be the easiest. And easy is important in this one because not everybody's going to be an energy codes expert. So my colleagues in the planning department, or my former colleagues in the planning department, might have wonderful intentions. I don't want to see them try to finagle an engineering solution. That is not their layer of expertise. They're not going to know what they're doing, and they don't have the sufficient information of when they're looking at it to have any kind of semblance of direction for that. So, tiered codes give a very organized and very systematic way of evaluating something's energy performance. So what are these tiers? If I just mention them, let me just very quick. You can read all these. I think the most important ones are 4 and 5 to me. And just the idea of scalable energy performance means Tier 1 is worse than tier 2, which is worse than tier 3, which is worse than tier 5, or 4 or 5. And the beauty is all of those tiers were established at the national level to result in the highest tier being what we call net zero energy ready. And that doesn't mean I have to put solar panels on, but it means if I put on a renewable energy source, my expectation is that building has reduced its consumption to the point where it should be close to break even. Second one, and probably the most important one, it gives you a way to measure the stuff that is consistent, accurate, and authoritative. I always joke about this whenever I talk to my consultant colleagues about NECB. If I run my house at 7 degrees C and never turn on the lights and shower at work, I have a net zero energy ready home, regardless of what I built. The problem is the next family that moves in that has 3 teenage daughters who all take 30-minute showers and decide that they want to watch TV a lot and run it at 24 degrees, it's not even in the ballpark. So I can't look at someone's utility bill and go, you're net zero energy ready. Can't do that. That's what this is. All of the rules in the energy codes effectively just are ways to make sure you are talking about the same thing in the same way. So it makes for apples to apples comparisons between buildings. A couple things that are in and out of scope. It only measures operational energy. So that is the energy that is consumed by the building in its operation. It does not talk about greenhouse gas emissions. And I say for now because it's building those out as we speak, but today it's just operational energy. It doesn't talk about renewables, and it doesn't have other sustainability objectives in there. It doesn't talk about water conservation unless it directly affects energy consumption. So it's not a broadband sustainability policy. It's literally saying, hey, let's look at the energy that's consumed by your building. With that said, let's go to the Municipal Government Act, because the Municipal Government Act is another piece of legislation that cities use that sets out a lot of the important stuff that deals with the development permits. So anytime you hear the word bylaw or zoning or development permit, you are dealing with some iteration of the Municipal Government Act for the rest of your careers. I just got to point this out. All buildings need to comply with it, whether you need a DP or not. For instance, the City of Calgary, if I'm building a house out in the suburbs, I don't need a development permit, but I do a bylaw check. It's actually what it's called because you have to comply with those. It covers a lot of things, but the most important thing I think that it needs to understand is it regulates only to a certain point. So it talks about huge implications for buildings, what they're worth, how you do it, how far back from the curb they sit, how tall they can be, how wide they can be, what their use is, all those things. But they don't talk about the technical matters of a building, and that's why we have to have this part in the Safety Codes Act. And that Section 66 of the Safety Codes Act is kind of infamous because it says something that's really interesting. The MGA says, as a municipality, you can put in place bylaws. The Safety Codes Act says, yeah, go ahead and put in place bylaws until it starts to affect things that are governed by the building code. So it puts a very rigid line in place that says, you can set a bylaw that talks about pets. You can set a bylaw that says how tall the building is. You can put a bylaw that says you can't have this use within 300 meters of this use. What it can't say is you are going to build to this level of energy efficiency. You can't not follow the building code. If I try to write that bylaw, the province will have me in court before the end of the week. Literally, there's no other way to describe it. And it's important because it was designed as a catch-all, saying, if I'm the economic officer for Airdrie, hypothetically, I can't go to a builder and say, you come to Airdrie and I'm not going to enforce the building code and save you $50,000 on a building, because that was deemed unsafe. So it's there for all the right reasons, but it sets up a very strange tension between the Municipal Government Act and the Safety Codes Act. But again, there are a lot of parts of buildings that are not regulated in the Safety Codes Act or under the building code. Zoning, setbacks, building heights, FAR is floor area ratio. That's the amount of built floor area compared to site. That's all it is. Site coverage, how much of the lot you can cover with building. And this is the big one. Doesn't cover incentives. Which brings us back to this question. As I said before, please put a pin in that. Because if the question really is, how do you get somebody to voluntarily build better? I'm not entirely sure that isn't part of the answer. I can't make them do it, but I can encourage them to do it. And it's a little different than governments are used to doing. Governments are very good at saying, do X, not Y. Done. We're not very good at saying, do X instead of Y, because it's a little bit more, again, it's a little bit more complicated of an issue to do that. We're going to go through this pretty quick, because I don't know what we're doing for time, but I think we're probably running a little bit longer. Some of the things, we'll probably have these up when we ask you for your feedback. You can talk about bonus density. You can talk about policies requiring new development to meet higher tiers. How is that different, by the way, than saying you must do it? That's an option. If you want to build that building, you have to do this, or you can build this building without doing it. You can expedite permits. Okay, time is money. It's literally in buildings because they're all financed. You can put levy rebates on things for doing the right things from an environmental perspective. You can certainly talk about temporary tax reductions and financing things through SAIT. The ones with stars, by the way, are things we already do in the city. So those have already been legally tested and been found to have been okay. So there's a lot of ways to get around this legislative thing. And this we put this together, my colleagues and I, because we just want to kind of look at certain things where, again, think back to that simple flow chart that goes owner, development permit, building permit. How do you treat those three objects to work together to get better buildings? And so all we did here was basically run a couple scenarios that talked about saying, well, okay, what happens if the city of Calgary sponsors the building? Well, as if I'm paying for part of your building, I'm effectively part of the ownership team. I can put a requirement into the contract that says you will build to tier 3. That's my choice as an owner. There's nothing legally, there's nothing they can say about that. You've signed the contract that agreed that said this building for this price is going to deliver this level of performance. It's different than me walking up and saying, no, you must do that. You can put in place incentives to talk about this. You can talk about how to just give owners the right tools to do the economic analysis to reach better building conclusions. But again, we'll probably keep this up as we go through the next task. I'm going to put a pause there just for a second to see if there's any quick questions. That's a lot of legal talk. Now, again, I hopefully have given you the layman's terms of this. I'm not going to pretend to be an attorney, but what I really want you to take away from this is the legal framework is not cut and dry, and it affects different parts of the process in different ways. But that's kind of what you need to have knowledge of in order to capitalize on any of it. Any questions? I don't see any. Okay. The other part that I think you need to know in order to really start to understand energy codes in general, you have to understand basic energy. I can't realistically talk about an energy code without understanding energy flow in buildings. You just can't. So we're going to come back to this thing a lot. This is the typical energy consumption. This is amortized across Canada, but it's basically where the energy in your house goes. And there's a couple things that should probably, be important. Number one, the red and the orange are heat and hot water. By far the biggest component in a residential building. It's not even close. Because that is, what I'm just going to eyeball it, 80%. roughly, of the energy consumption in a building. What does that mean? It means somebody selling me a slightly more efficient air conditioner under the premise that it's going to save me a lot of money is lying to me. That's what your takeaway should be. But it does say if I have a 40-year-old furnace in a house that has a $400 a month gas bill, and I can get another 15% efficiency by upgrading it, that's probably worth my time. I would happily sit down and go through the brochure with the individual who's selling me that furnace and go, that makes sense. We have to do a little boring physics on this because I'm going to go back one. If this is the big part of the problem, then we better understand what the fundamentals of that part of the problem are. And that means we have to do a little bit of physics here. So first thing, I'm going to make a statement everybody understands, but very few people apply. Heat has to flow from hot to cold. Okay? Which means in our climate, pretend this is an outside wall, humor me for a moment, I'm generally losing heat through walls and windows. There's a couple days out of the year where I will gain it. And yes, I do get solar heat gain even when it's minus 30 if my windows are arranged correctly. But the vast majority of the heat is going that away through the wall. The second thing to realize is it's going through that wall in 4 ways, which is something most people don't think about. While the first statement's obvious, the second one probably isn't. We have conduction, convection, radiation, and advection. So conduction, heat flow through a solid, okay? That's why your drywall is cold. That's why that's heat's going through the wall. Convection, movement of fluids to carry heat. So whenever you feel that draft in the wintertime by your window, it's often just cold air that is flowing down the surface of the window. That's the actual draft you feel. It's convective current. Radiation, I know it sounds complicated. It's just the emission of thermal of infrared heat over a body. Entirely dependent on temperature, just does what it does. Last one is advection. It's a fancy word for saying something that's quite obvious. It is the transfer of heat by carrying mass. So the example I always use, if I take a pot of boiling water outside and leave it there, I have not only carried water, I've carried a wicked amount of heat with that water. So while buildings don't typically carry water outside, they do leak air. So the way to think, whenever you see the word advection, air leakage. So you're taking hot, moist air from the inside, and it's leaking to the outside. I should back up for a second. In case you're wondering, this one and this one is what the code focuses on. Whenever you hear R value in a wall or U value in a window, it's just a measure of the conductive heat loss. When you hear air tightness or blower door test or air leakage, you're talking about advection. That's it. That's all. There's your, if you take nothing away from today, know that that's what the energy codes really do focus on. And why? Because they're 90% of the problem. I do have to point out, if I take a window, windows are really interesting because they've got all 4 in spades. And that's why I always use that because it sounds abstract to talk about radiation in a building. But take a window. So I'm going to have conductive heat loss through the individual sheets of glass and through the frames and the sashes. Right? It's solid. Heat loss is coming through those. But I also have advection because I have air leakage around the frames, right? Air, depending on how well the window is installed, the transition between the window and the wall. I'm also going to have, if you ever look at your house, most people have double pane windows. You ever notice how consistent the spacing on those is? It's not an accident. It's because you don't want a 4-inch gap between those because I will set up a huge convective loop inside that window. They are actually spaced like an engineered amount apart, and it's usually between 10 and 12 millimeters, to optimize the loss of conduction without forming convective loops. And the last one is radiation. So whenever somebody talks about a low E film on the glass, we've all heard the term. The E in that low E is emissivity. You know what emissivity is? A measure of how broad the radiation spectrum emission is. it's a shorthand for basically saying this is how you measure the radiation emission for this. That's it. One window, all four. I always think that's kind of neat. I'm going to go through this real quick just because it's just backgrounder, but R value is important because it's a thermal resistance for conduction. U value is the way of measuring thermal conduction, but it's the inverse. And that's the relationship. And I can't tell you how many times when we were talking to industry when the energy codes first came out, that was a big part of it. How you measure those things is critical. So understand that you need to be looking at RSI and USI values, and that RSI, the better performer is when the number goes up, and USI, the better performer is when the number goes down. And yes, I'm not going to apologize for it, but that's 100 years of industry convention. And it's really interesting. I can tell you, I hate to be blunt, contractor, engineer. That's literally the way to divide it up. Engineers love U values. Contractors love R values because they're intuitive. U values are easier to calculate or using calculations. The other part I just want to make clear on these things is think back to that circle we showed where the space heating was 80% of the energy consumption. These, I love and hate these kinds of diagrams. I love them because they're good at simplifying complicated things. I hate them because they're extremely misleading. And they're extremely misleading for one simple reason. Okay, I can talk about drafts being 12%, right, of the energy loss, or walls being 33%. What happens when I put in better walls, though? It no longer loses 33% through the wall. So not only do I shrink the size of the circle, to use that analogy again of the energy consumption, right? I actually change the proportions of where this stuff goes. That is why when we talk about code compliance, the vast, vast majority of people don't want to use prescriptive. They want to use a performance model. And what a performance model does is basically understands that I can not only change the amount of energy this building is going to consume, but I can also tweak where it's going. And by being able to tweak where it's going, you can often get enormous performance gains. So that's important because, allow me to give a very simple analogy. If you have a house that's built after about 1995, you're almost assured to have 2x6 walls, bad insulation, and windows that are somewhere, like you'll have argon-filled double pane, like usually in some kind of wood frame or metal-covered wood frame. It's just what we built for 30 years. The R value of that wall is going to be somewhere in the neighborhood of R17 effective. Okay? The window beside it is going to be about R3. What does that mean? It means I am losing 7 times more heat per square foot of wall than I am on a window. When people talk about how to upgrade a building, if you don't understand that this changes things, the chances of you guessing right are just about zero. And there's an entire industry, energy auditors, energy advisors, any building envelope person who's worth their salt, home renovation guides, deep energy retrofit corporations, whose entire job is to figure this stuff out because it's not intuitive and it's not obvious. But it is so impactful for where things go. And it also ties into what problem are you trying to solve? Because if my house is drafty, I have to understand if the draft is coming because I have bad weather stripping, or if the draft is coming because I have bad windows and it's creating a convective loop in my home. You can test for those, but if you don't know to test for them, you're probably not going to guess right. Let's say abstract parts of this. But again, I'm a firm believer in if you tell me what, where, how, and when something works, I'm probably still not going to do it until you explain to me why I'm doing any of it. And this morning was really a lot about the why and all this stuff. What's its framework? How do I use these things? Why would the federal government have spent literally millions of dollars and hundreds of thousands of consulting hours to build tiers? That's a big investment. So I think we covered a little bit of that today. What I'd like to talk about now is let's get into the code just a bit. And again, my goal this morning is not to walk you through all the technical requirements of the code. It's available online. It is free of charge. We're working with the city of Calgary to build an entire compendium document, like a manual that says this is how you measure this. This is how this should look. This is how the parts fit together. This is how an energy modeling report should look like. We have all of that stuff there, and it's long to go through because it's a lot of technical requirements. But we do have to touch on certain aspects of the code, and because I think it's really important to see how codes change over time. And again, like if you recall back to one of the things I pointed out when we talked about the city charter saying you need a climate change adaptation and climate change mitigation plan, one of the requirements was, and you got to go back to it every 5 years and fix it because you're not going to get it right. Codes work the exact same way, right? We are constantly rewriting codes. I guess I never actually introduced myself this morning. That's kind of funny. I'm Justin. Hi. One of my side hobbies, in case you're wondering why I do a lot of these presentations, is I actually sit on the committees that help write all these codes. So if you ever can't sleep and need to be put to bed and you decide to break out your NECB, if you look at the authors page, I'm on there with a bunch of my a number of other people who sit on the committee. Back in that day, for that iteration of the codes, it was the Standing Committee on Energy Efficiency, and now it's I'm not even going to get it right, but there's basically the Codes Commission on Mitigation, Adaptation, and Climate Change. So basically, they've reframed the exact same objectives of how do you make buildings more energy efficient and give them a new structure. But I keep going on writing these codes because they never change, or because they always change. It was exactly the opposite of what I wanted this. And they have to change over time for a lot of reasons. Performance goals change, technologies change, and governments do things like they put in place a heat pump incentive. All right, if I'm giving somebody $5,000 to put a heat pump in their house, I better know what it does. And that's just called responsible government spending. So it's good that they kind of finance and understand all of these intricacies. And that's what we're going to talk about today. So again, this isn't a deep dive I don't want to sell you a false promise that says once we've gone through this next half an hour, you're going to understand how to be an energy code advisor. That's not going to happen here. But we will point out all the links to all the stuff that can actually make you a pretty darn good safety codes officer, or at least the beginnings of an energy advisor with respect to energy codes. So let's talk about this thing. So first things, we got a couple things. Number one, I got to point out energy codes are always structured by building system. It doesn't matter if you're dealing with 936 or NECB. You are always dealing with systems. So in 936, so that's the one for housing and small buildings, we're talking about building envelope is 936.2, HVAC, you'll see that term a lot. That's heating, ventilation, air conditioning for people who aren't familiar with that word, although it's pretty common. 936.3, service water heating is 936.4. So those are all the technical requirements. So that is, if I'm following prescriptive and I just want to do what the book says, this is going to tell me what the efficiency of my hot water tank should be. So it's the kind of things you can check on a boilerplate and go, yep, you've done your job. This is where energy codes get different from everything else. 936.5 is performance compliance. That is how to set up an energy model to demonstrate that your building performs as well as a prescriptive would have without having to do any of that stuff. Indulge me for a second. Remember that house with all the arrows that showed the energy flows? Those energy flows are figured out by doing an energy simulation. So at any one point on that building, I can take a chunk of wall, okay? And it depends on how the software you use, but it's either going to be a square foot, a square meter, or a square centimeter. But I can look at that chunk of wall, and in the minute I know what the inside temperature is, what the outside temperature is, I know how much heat's flowing through that section of wall. And then I do the same for a window. And then I look at the lights and say, okay, the lights are on at this point, and they're going to give off this much heat, and it requires this much cooling to deal with it. And if I do that, here's a weird number, 8,760 times, I'm going to have a pretty good idea of how that building works over a year. Where does the number 8760 come from? That's the number of hours in a year. So what an energy model does is essentially this. Every hour, I'm going to figure out if the lights are on, if the furnace is on, what the inside and outside temperatures are, and where the energy is going. And then I'm just going to add it all up. And the beauty of doing that is I no longer have to follow a single rule. But what I do have to do is be very diligent on how I've done that calculation. So that's where this separates out, because there is no equivalent in the life safety standards. So I'll give you an example. Part 3 of the Alberta Building Code, right? If you look up exit corridor, the number is 1,100 millimeters. Not 1,100 millimeters if there's 25 people in the room and 1,200 if there's 55. Or show me that I can go down a corridor that's 1,000 millimeters wide if it doesn't have any rough surfaces. It doesn't say any of that. It's 1,100 millimeters. That's how you comply with that code. It's entirely prescriptive. This is the one that says energy is not the same as that, because energy systems aren't additive. And if I was to dumb it down really simply for a lay person, these are fluorescents. I'm going to throw somewhere in the neighborhood of 30 watts into these tubes, okay? Of that 30 watts, I'm going to get a certain amount of light. I'm also going to get about 22 watts of heat. The building has to deal with that heat. It either goes into the space as supplementary heating, or in a room like this, because it's not losing heat anywhere, I have a cooling system that has to pull that out. Or this room at the end of the day is going to be 45 degrees C. And that's uncomfortable. So you have all of this interdependencies in an energy simulation that really need to be well-versed, is the way I would phrase it. The red ones are new sections. So this is, as I said, codes change. The red is all the new stuff. Air tightness of building envelope. Huge change from the last one. I hate doing this, but just to show we haven't all wasted our time together this morning, could somebody yell out what the heat loss mechanism of air leakage is? I see somebody mouthing it. That's good enough. It's advective air. It's advective heat loss. But this has become a big part of it. And again, think back to what I was saying this morning about the proportions. Why? Because we've gotten good enough at the envelope that air leakage has started becoming the biggest part of the energy loss. That's why it has to be improved. Here's the tiers. There's 2 ways to comply in 936, and we'll go through those at a little bit of depth because, well, frankly, that's why we're here this morning. Let's look at some of the changes in the building envelope. We'll just do this very quickly, capture a couple of key components that are really fundamental to understanding the tiers, and a couple of key features that are new. We'll go back to this guy. There's my energy loss for my building. As I've said, circle can get bigger or smaller depending on how overall energy efficient the building is. The proportions can change. The one we're dealing with now, building envelope, affects directly space cooling and space heating. So somewhere about 2/3 of the energy. If we were doing the compliance one, I would say from a 936 perspective, that's where I would spend at least 3/4 of my time if I was a safety codes officer still. I'd be worried about the envelope because it's the biggest chunk of the energy puzzle. A couple things that are in here. You can read this. These are really, I'm assuming we're going to distribute this afterwards, the presentation. Okay. Read these at your leisure. It's probably not worth us going a very big, but everything from updates to log walls, who cares, to changing the rules around Part 10. So fundamental concepts of building envelope is really simple. We break the building envelope down into parts. And that's important because not all parts have the same ability to get upgraded. And I probably didn't mention this earlier, but I should. Whenever we make a code change at the national level, one of the things we are obligated to do is a cost-benefit analysis to it. And that's a big part of it because housing affordability is a big concern for everybody. So to double up the insulation on a wall is a lot more expensive than doubling the insulation in an attic. Because doubling the insulation in an attic is just a couple more bales of blown-in insulation, almost free. Well, last time I bought it, it was about $28 a bale. Doubling that, you're going to spend on a small house a few $100s. Labor's about the same. That's nothing. If you want me to wrap a house in styrofoam SM, that's significantly more money. So I guess what I'm getting at is it's not all, you have to break it into systems for two reasons. They don't all behave the same with respect to cost-benefit analysis, and they don't have the same amount of heat loss to them. Okay? Everything in an energy code is effective thermal resistance, not nominal. We'll talk about that in a second. This is a huge one. And if anybody is ever working at NECB, you will know that this is a huge one because it changes everything. FDWR, fenestration door wall ratio. That probably still doesn't mean anything. Think about it this way. Fenestration and door. Fenestration is your windows. Doors are doors. Wall is the opaque sections of a wall. So the stuff that's not a window. And the ratio is the percentage I can have of each of those. Why is that so important? Because as I mentioned earlier, a window is about 6 times more thermally conductive than a wall. So if I have to reduce energy consumption on a building, one of the fastest, cheapest, technically price positive, well, one of the things I'm very tempted to do, make the window smaller. Go look at a research station in Antarctica, and they just have these little portal windows because that's all they can afford in terms of the thermal losses. Last thing, there is a lot of flexibility in this code, more than any other parts of the NBC. And that flexibility is both a positive and a negative. It's a positive in the sense that it does give you a lot of compliance options. It's a negative in that it is much more complicated to write a code with options. It's very easy. We'll go back to that corridor. It is really easy for a building inspector to go, is this an exit corridor? And when somebody says yes, to go to the tape measure and go, yep, it's 1,100 millimeters or more bigger or wide. That's an exit corridor where I come from. It's a lot tougher to say, oh, I've improved my windows, so I've degraded my wall, and at the same time, I've improved the efficiency of my hot water tank because I didn't want to use a heat pump in my heating system. Well, wait a second. Now I've got 4 things all talking to each other. That's a very complex code from that perspective. This is just a little handy-dandy guide, and we're not going to go into this in depth. But as an indicator of how many parts there are, the CHBA actually put this diagram out that said, let's understand something. The wall that's below grade transfers heat differently than the wall that's above grade. Why? 2 reasons. Number one, I'm allowed to keep basements at a colder temperature in the code. They actually only have to be heated to 15 degrees, whereas upstairs has to be 22. Second part, this dirt 8 feet down is only going to vary between maybe 0 and 7 degrees C. That's the thermal driver. This air can go between plus 35 to minus 35. Huge differences. If I'm going to construct an energy simulation, I need to know all that stuff. We haven't even gotten into the fact that if this wall's in sunlight, that skin temperature is not air temperature. That skin temperature might be 60 degrees C. So on the coldest day of the year, I might have heat coming in on that wall, and on the north wall, I am losing heat at a huge rate. So you can understand how, again, the complexity of this can come back to it. But in general, you're looking at things are either defined broadly as in contact with ground or not in contact with ground. And I know it sounds funny to say a floor not in contact with ground, but what that's saying is it's code language for a cantilever. Windows are separate, roofs are separate, and they're broken down to attic roofs and cathedral roofs, but you basically break the envelope into chunks, is what you do. And they each have their own requirement. All of those RSI values that are in the code are effective, as I mentioned. An effective R value means not the nominal, but what does the assembly get? Okay, that is a calculation. No, what? I mean, I've been doing this a while. I can tummy rub and get you close, maybe 5 or 10%, but nobody knows exactly what that translation is. We'll talk about that in a second. But the nominal is basically this. When you see a bag of insulation on site or the styrofoam SM printing on the side of the material, it's a reflection on the material. The effective R value is how that assembly behaves. So it understands that I've got other components that contribute to thermal resistance. I also have bridges or breaks in the insulation that say, oh, that's going to be a degradation. And you have to calculate that out. There's no other way around it. I wish, I always say this to my colleagues my former colleagues at the city, I wish I could tell you one was always bigger than the other. I can't. It depends on the insulation type, where it's placed, if it's an exterior continuous or not, et cetera, et cetera. Basically, this is just a quick comparison between nominal insulation values and effective, but I do want to point something out. They can be vastly different numbers, especially if you're dealing with steel and concrete buildings. The minute you put steel in a wall, I have an almost perfect thermal conductor. Almost perfect. And to the point of, if you actually look at steel studs, that's how they're calculated. If hypothetically, if this blue line is the steel stud, not only do I worry about what the insulation is here, I actually have to zone it out because this thing is so conductive of heat, it will draw heat laterally into itself through the wall. Concrete's not a whole lot better. As an indicator, just good rules of thumb. If I'm looking at insulation or anything that's readily available, I'm looking somewhere between R3 and 5 per inch. Okay, RSI, or R, thermal, like imperial R. Wood, about R1 per inch. Concrete, about 0.1 per inch. So about 10 times more heat conductive than wood. I go to steel, depending on whose numbers, but it's generally 0.0000 something. About 1,000 times more conductive than wood. Yeah, those are non-trivial numbers. Like you can't put a giant chunk of steel in a wall and go, I don't see a difference. There's the difference. When we talk about all of these things, one of the things that is really interesting in this, the presence of an HRV. HRV, heat recovery ventilator, you may have heard of. You also get the term ERV, energy recovery ventilator. It basically means it's a power device that pushes air in and out. It ventilates the building, hence the ventilator, and it has a heat recovery component to it. When you are looking at this, you have to understand that the R values are going to change whether or not there's an HRV. That is unique to 9.36, by the way. But it's important. And the reason it's done, I can explain, it's the logic path that led to it is HRVs are not not mandatory in 9.36. So what they wanted to do was say, well, how do I set up an equivalent level of performance between a house that has an HRV and one that doesn't? And so what they did is they modeled the HRV houses, and then they made you add additional insulation if you don't put in an HRV to compensate for the heat loss through the ventilation system. So it was an attempt to balance this stuff out. Why? Because code should be intrinsically fair. They're not, but that's what they try to do. But I just want to point out a couple things. So this happens to be without, but again, when I said because certain parts are easier or harder to insulate, you'll note that you are required to put about 3 times as much insulation into an attic as you are to a wall in a house in Canada, in our heat climate zone. The other thing I should point out, just because it might be a new term for some of the people here. The concept of climate zone and heating degree day. If I use heating degree day, can I get a quick show of hands? Does that mean anything to anybody? A few. Let's take just 30 seconds. Heating degree day is a number, okay? And that number is going to range in Canada somewhere between 2,800 and 13,000. What does it tell me? It tells me two things. Effectively, it's a measurement of how cold it's going to get and how long that cold is going to last. So basically, the larger the number, the more coldness I can expect. Coldness being both temperature or duration or both. And it's just a calculated number. And it's, if you ever can't sleep one night, Appendix C has hundreds of locations across Canada and their heating degree day zones. So it's just a way of measuring basically the climate you're in and where your building's going. Calgary just happens to be exactly 5,000. It's an easy number to remember. Zone 7A. Again, this is just to demonstrate the change in the values. That was 10.43 without an HRV. It drops by over a full point because you put in an HRV. Just in case you're wondering, again, I always like to tell people to stick a pin in an idea. This is going to be, when we come to the next set of questions, we're going to talk about cost benefits of these things. This should be a big part of it because this entire change of numbers, that is dollars driven. Nothing to do with building performance, nothing to do with the mechanics, all of it to do with dollars in and how much you can change something in a building. Windows. Windows have two ways of being measured in here. So they have, as I mentioned, Windows use U value, not R value, so the inverse of it. So the smaller the number, the better it's performing. And because the window manufacturers can never make Windows simple enough, they've also given us an ER number. An ER number works the exact opposite, where the larger the number, the better it performs. But what this is trying to capture, in case you're wondering, U value is a measure of the conductive heat loss. ER is an attempt to capture the conductive heat loss, air leakage, and radiation. I personally hate it, but that's an opinion. That is, and the reason I don't like it is because the ER number would in practice change if I go from the north side of a building to a south. And you'll note there's no criteria on this. It's not 25 if it's on the south, 21 if it's on the north. So it's a little bit of a, I do this to represent tummy rub engineering, but it's a shorthand way to try to capture a very complicated issue. It does so with moderate success. Air tightness. Here's where we start to get into the air tightness journey. Now, for those looking to comply, or for those who are going to be using the energy code, air tightness in 936 is in two locations. One that is basic principles, the other for specific applications. We'll cover both. This is the general principles. So one of the attempts to address air leakage in NECB, or NBC, pardon me, is you have to do a certain amount of detailing in the construction. And 936.229 sets the criteria. 936.210 tells you what to do. The challenge with all of these things is how you measure air tightness, because without doing a blower door test, it's all a bit of hocus pocus. So if I'm doing prescriptive, 925 is what covers basic installation of air and moisture barriers, okay? So it talks about how you use polyethylene sheet, where it goes in a wall, what you would do with the joints, etc. 936.210 then tells me, okay, at that joint, I have to have these criteria. So you have to read the two of them together. You also have testing options. Again, because we can never make things simple enough in an energy code. 742 and 2357. I'm not going to bore you with the details of those. They are assembly tests. So what's important about an assembly test is twofold. Number one, it has different performance values, okay? Number two, it has a set of details that talk about the transitions. So what you may have noticed, the common thread between all of the prescriptive air barrier requirements in 9.36, this tells me how to deal with transitions. This tells me what the air leakage around a detail at a transition is. The common point of both of them, the transitions. Why? Because buildings do not leak at the flat parts of the wall. Okay? Glass is a great example. No one thinks about it, but glass is an absolute perfect air barrier. At where my finger is, I get exactly 0 air leakage. I don't care what pressure is until the window snaps. What about here? What do I do with the transition? That's where, I was going to say that's where 99%, that is where 100% of the air leakage occurs, is where you have junctures and joints. That's why what is interesting about all of these, nowhere in the code does it talk about quality. That's a problem. It's why we will, when we talk about the other place where air barriers are described in the code, 9.36.6, it tries to address quality, or at least how you might deal with that. Because the quality of that transition is everything if it has to be airtight. I can take the exact same materials, apply them in the same way. If I do one sloppy and one well, the air leakage will be 10 times greater in the sloppy one. And I'll share an anecdote as an idea of how complicated this is. At one of the meetings at the standing committee, we had a representative from CHBA. We were trying to figure out what the cost of better air barriers was. And they pegged a number that said, well, that's a $3,000 per house cost. And I threw my hand up and said, it's a zero cost. And they go, how do you figure that? And I said, it's in the code of what you should have done. And the reason we had such vastly different numbers on what it should cost, they were putting a value on the time it took to do the quality. My position, right or wrong, was that the quality should have been assumed because it's in the code. There is no right answer to that, by the way. I don't know what it costs. It might cost somebody $15,000 because they have to go from being completely inept to being fantastic at it. It might cost somebody nothing because they've been doing it all along. That's the trouble. Like, I'm belaboring this point just a bit because it really sums up a lot of the energy code challenges. You've told me to do this, but because we've built the system that allows flexibility, now the quality of the installation starts to become a real challenge. We've probably beaten up envelope enough. Let's go into HVAC, and should be relatively straightforward. Again, affects the exact two same areas: space heating, space cooling. Why? It's the equipment efficiencies to heat and cool your space. It does not affect water heating. I know it sounds obvious, or some people think it should. There's a whole different section for hot water, so left that out. But I guess, again, as an indicator, if it helps, part of the reason I always talk about when we do the compliance discussion with the City of Calgary, it's basically shorthand. Pick your battles. So if I can look at the building envelope and the heating and ventilation equipment efficiencies, right? That's two pieces of equipment. It's your HRV and your furnace, basically. And I can look at the walls and the air leakage test. That's four numbers I have to look at. And I'm going to roughly cover 2/3 of the energy consumption in that building. Why would I look at anything else? Like, if I have X amount of minutes to spend on this drawing, don't spend them looking at the cooling. Like, it's just not going to help you. Let's figure out the big ones. And there have been very few changes to the HVAC requirement in this. The way to read these charts prescriptively is actually pretty straightforward. It's basically a sizing and efficiency exercise. So all you really have to know, what is the piece of equipment? And there are hundreds of them. Or dozens anyway. There are dozens of them in the code. Okay? It'll have a size requirement. Why? Because bigger equipment is often easier to put more efficiency measures on it. And it's also going to be, because you're producing so much, you're consuming so much more energy, we expect it generally to be a little bit better at what it does. And the last part, just the metric of how it's measured. And the beauty of all of this, on the boilerplate, on the piece of equipment boilerplate. It's one thing to look at. Service hot water, that's the other kind of major component of 936. What a shocker. It affects your water heating system and your energy consumption related to that. A couple things. This is just, again, really more for general knowledge. Basically, the hot water systems in your home, which is different than NECB, but the hot water systems in your home, what they're trying to cut down on is extraneous line loss. So insulating pipes and making sure those are in place. Heat traps on the thing to prevent thermal siphoning, and the equipment efficiency. That's it. It's relatively straightforward. It doesn't go into elaborate calculations on the number of faucets, etc. NECB does that. It talks about your consumption. But 936 is like, I got 5 people here. I'm not going to change it much. And I can't control it. So let's just look at the equipment and the insulation. Same pattern. Tell me what your fuel source is. Tell me what your sizing is. And tell me what your efficiency is. Everything's on your boilerplates. Literally. We just gave a compliance session to City of Calgary. It's shocking how much you can review in 4 minutes on these drawings, because this is literally just a note somewhere on the mechanicals page. And it's super easy to confirm. And if it's a performance model, which we'll get into in a second, then I don't care. Then I only care that they've modeled it correctly, because I don't have to meet any of these in a performance model. This is all prescriptive. We're not going to cover it today, but I do feel the obligation to just say that quickly. Everything we've covered up till now is what we call prescriptive. Okay, so prescriptive follows that code rule that says, just do what the code says. As long as you've done that, you're gonna end up right in the ballpark. When I'm doing prescriptive like that, when I'm an inspector or a plans reviewer or a juryman for that, I know that if it's a prescriptive, these are the numbers that get checked. And what I call that in shorthand is inspecting to code. The piece of equipment that I find on site should match what the code is asked. In a performance model, it completely switches, because the performance model doesn't ask me to meet this number. It says that service water heater, in combination with that furnace, in combination with that HRV, in combination with these windows, this wall, this ceiling, and this orientation, overall gives me the right solution. So instead of inspecting to this on site, I have to follow what's on the drawings, because the drawings told the model what to put into it. The model shows me that they work in combination. So that concept of inspecting to code versus inspecting to drawing, if you're in the trades or a contractor, there's your massive takeaway from the morning, to be honest. If you can understand that conceptual difference of whether you're designing this to a code requirement or whether you're designing this to a drawing set because it's been modeled, that's really foundational. Just gonna grab a quick drink of water. Now, that brings us conveniently into the world of energy performance compliance, energy simulations. Okay? This is where, when we talk about inspection to drawing or inspecting to design, that's what this is applying to. So there's a whole bunch of changes that we've made here. The most important ones, I think, 2 pages worth, all hover around this. So understanding what has to be the same in a performance model. So certain things, building geometry, cannot change. Why? Because if I have a building that's twice as big, I won't use twice as much energy, but I'm going to use more energy. Size matters in buildings. Try heating a single car garage with a plug-in electric heater, and then go try and heat your house with that plug-in electric heater. See which takes longer. All of the envelope requirements, okay, they have to be specified and they have to match the drawings. HVAC and system and hot water systems. You get to design it in a performance model, but that means they must be designed. You must tell me what you're putting into it, and that must be maintained. Location, climate, and sun exposure. All of the things that I said, the ER in the window, the outside air temperature in that a wall faces, how much sunlight is on that wall, all gets baked into an energy simulation model. And I can't ignore them. They are too big of a number. I will give you an example from my own my house. I built a garage, and as an architect, you have to make it a little bit fancier. So I put up Corten rusted steel sheets as the siding on it. Looks great. That building, if it's even slightly sunny and minus 30 degrees out there, I can still literally not burn my hand, but get it hot at minus 30, because that sunlight on that south side of that building has picked up so much heat because it's dark steel. Like in the summertime, I can actually like make it like a steam show by throwing water on it. It's wild. But all of that it has to get baked in. And it's something you do not have to do in a prescriptive, but the minute you are talking about a performance model, you must close for those things. It's also why, to be really honest, it provides an enormous benefit. If I can give you a cheat sheet, if I owned a house building company, I wouldn't even think twice. I'd do everything blower door test, and I would do everything performance model, because I can pick up all of those fringe benefits you just can't get from doing prescriptive. There are, of course, exceptions. If the space is unconditioned, I don't care. Change it. I don't put any heat into it. Do I really care what happens to it? Probably not. Exterior lighting, again. Why? Because the heat dissipates the atmosphere. So how do you demonstrate compliance? It boils down to one simple sentence. I'm going to run two models. Reference, which would be a building with that geometry, that orientation, that fenestration, right? Built to prescriptive, and then the exact same geometry and orientation built to what I'm proposing. And as long as that proposed house, so as long as the design you want to build uses less energy over the course of a year from a reference house, it passes. It is in some ways the most honest way a code can work. It basically says, I've told you to do all of these things, but I'm not going to make you do any of it if you can show me that you can come up with a better solution. And it's funny because, again, I always like to tie this back to the life safety standards, because those are really well-established codes in Canada. This building's a good example. I should be at any place in the floor plate, I should be 45 meters or less away from an exit stair. And if you pace it off, I'm sure it happens, okay? It doesn't say 45 meters if I only allow people who are able-bodied into the space. And it doesn't say, but if everybody's a track athlete, I'm going to let it stretch to 60. It doesn't say that. What it does say is, there's your 45 for this occupancy type, go. What performance models do is essentially say, if 45 is what you're asking for, and we know the average person walks at this speed, it's this many seconds. Can I apply that many seconds to a different way of measuring it? Give you the same level of safety, but without following the 45. That's what a performance model does. And it's funny because the rest of the codes are slowly working their way to that standard. There's a colleague at the city is actually sitting on one of the committees that talks about rewriting all of the travel distance requirements in the code to make them performance-based, or at least how you would build a performance-based. So this is, again, in terms of takeaways, I think this is a really important one, just to understand conceptually what they're doing. I'm not going to spend too much time on here. This is just some of the things you have to be aware of. So fenestration door wall ratios, the equipment listings. This isn't a course on how to become an energy modeler. We can give you that course, but not today. Airtightness is a different story though. So airtightness, that's a misprint. That's on me. Sorry. It affects space heating, space cooling. Doesn't affect water heating. There is a whole thing about, so there's some fundamental changes in air barrier testing. Number one, there's the idea of performance levels. Okay? That's one of the fundamental concepts. The other one is this. When you get a blower door test, if I just say blower door test, does everybody know what that looks like? Okay, good. Then you're probably familiar. There's two common ways of doing it. One is you pressurize to 50 pascals. One is you pressurize to 75. I don't know if anybody's ever looked at the wind speed you need to generate 50 pascals of pressure on the face of a building, but it's like a 40-mile-an-hour wind. It's huge. So that really applies only on a few days of the year. So there is a correction feature in this now. But they're talking about, well, what does it leak at 5 pascals? That's what a building typically experiences. And so it's trying to make the models more accurate. And that's a big difference because, we'll talk about this in just a second, we'll touch on it anyway. Depending on how you measure these things, and again, it's one of those things, my first degree is in physics, I have to bore everybody with this. We think of air as being this weightless, flexible thing because we're so used to it. But air has weight and it has viscosity. So if I have a hole this big, right? And I'm going to make up a number, 2 square feet, right? Or I have 10,000 holes this big that total 2 square feet, the airflow through those two different things at different pressures is night and day. Literally night and day. And don't get me wrong, there's aeronautical engineers who spend a career writing PhDs on how to calculate that. It is not simple. But just trust me, because air has a thickness and a viscosity, it doesn't want to flow through 10,000 little holes the same way it does through one giant. Think about a building now. We rarely have a place where somebody forgot to put in a window. That usually gets picked up on the site inspection and says, Doug, you missed the window. Put it in. But what you do have is 10,000 little holes in the air barrier because of the quality of install. That's what makes it really complicated. The other thing that is intrinsic to air leakage is the building durability aspect. I always joke, if anybody asks me why it matters to me, like as a former safety codes officer, in my career at the city, I worked there for almost 15 years, over 15 years. I saw one structural collapse, and it was due to a building got undermined by an unmarked stream. It's the only time we ever saw a structural collapse in my time in there, 15 years. We had one wall failure of a structural angle in a commercial building. So 1.5 structural failures in 15 years. Go talk to Alberta New Home Warranty about how many complaints they get for attic rain, mold around windows, and drafts. Because they spend millions of dollars every month going to investigate all of this stuff. The building codes have been around long enough that they are pretty good at preventing massive catastrophic failures. What they're not really good at, to be honest, is preventing somebody from forgetting to connect up the bathroom vent and having a bunch of hot, wet air dumped into a cold attic and basically creating a mini rainstorm every spring. That's where your lawsuits happen. That's what you're going to get sued on. You have to miss an awful lot of 2x4s for a building to fall down. You have to miss one taped joint on a bathroom vent to have that problem come around. What do you think's more common? This is just an illustration. Air leakage, yes, not surprisingly too, but okay, we've got air leakage, more energy consumption. Watch out for the gaps of transition. Covered that already. Determinations of this stuff. there's a lot of ways to look at this. I just want to point out something. There are now 3 ways to measure air leakage. Air changes per hour at 50 pascal, normalized leakage area at 10 pascals, and normalized leakage rate at 50 pascals. You don't have to worry about which one you're going to meet. That's for your energy advisor to take care of. Just be aware they're there. And the reason we have this is when we get to tier codes. So all of these represent a different amount of air leakage and energy loss related to air leakage. And we needed those because of where we're headed next, tiered energy performance. So 2 ways to measure to comply with tiers in 9.36. First, performance modeling. So just so you know, about 2/3 of the 9.36 submissions we see in the city of Calgary use performance compliance for all the reasons I mentioned earlier. Because of that, logically, they built a tiered system around that idea. The good part is you basically do exactly what you did for a performance model. You just have to report the numbers in a slightly different way, which is good. But credit where credit's due. Tiers in the code ask you to change almost nothing about the way you do things today, which is really smart. Because if you were asking me to change my ways, it's probably almost impossible to implement. But what it is basically this. I'm going to have 2 size categories. Talk about that in a second. I basically have anywhere between 100% of the energy consumption all the way down to 40. They correspond to different tiers. And if I'm using 40% of the energy of the building, I consider that net zero energy ready, my highest tier. So all I do is I report, remember I said, in order to comply with the performance model, performance simply has to use less energy than reference. This just tells me how much less I have to use. That's it. 1 additional calculation is all I need to do to comply with performance tiers. I do it the same way. I build the same model. I can build it however I want. Again, it doesn't take any intrinsic flexibility. It just says, instead of the target being 100% or up to 100%, now it's up to 40%. That's it. Prescriptive path. I sometimes joke about this. I've told my colleagues, I will happily buy them lunch if they can find me somebody who does this more than 5 times a year. But we built a points system for prescriptive compliance. And we'll break it down really simple. They haven't done tiers 3, 4, and 5 in 9.36 because points at those levels of performance are really challenging. And when I walk you through the tables, I think you'll understand why I say that. Essentially, if I have 0 points or less than 10 points, I'm doing tier 1. If I have 10 or more points, I'm doing tier 2. So what are these points? Because that's probably the next reasonable question. I get points for doing things in excess of the prescriptive requirements. The process is identical. The calculations are the same, what that says. I just have a different expectation of performance. So, for instance, let's look at above grade walls. In our heating zone, if I do 297, and when you go to the code, 297 is exactly, RSI value 297 is what you will get to do basic code compliance. Not surprisingly, I get exactly 0 points from meeting code. Kind of makes sense. If I go to 308 with an HRV, I get 2.1 points. 369, 6.7, so on and so forth. Now, why does this get complicated? 2 reasons. Number 1, by adding all of that additional information and calculation, probably costs me more than just doing a performance model. So that's why I think tiered performance is going to be the way to go. But the second part is, you will notice that these are not continuous across any row. And the reason being is this all had to be done on model data that realized that in a different heating degree day zone, I have a different baseline. So you end up with this weird system where I can extrapolate vertically in a column, but I cannot do so horizontally. And most things that I can extrapolate in a code, I can do that. So limiting distance is one that's famously done for extrapolation. And what you do is you literally say, okay, once I'm this far from a property line, I get this percentage of unprotected openings. The next number is this. I can just assume a line between the two. Let's do it. This isn't linear. This can't be extrapolated for heating degree day zones. It's a really weird thing in that sense. That's, I think, part of the reason you're not going to see a lot of it. But in an attempt at fairness, there is one for envelope requirements. There's another one for fenestration, so windows. Same idea. Doesn't talk about the area of the windows, just talks about the performance of the windows. There's one for, what is this one? The low-grade walls. This one is for air tightness. So this is where, if you recall just a minute ago, I said, here's the air tightness levels. That's why we had to build all of this, because I have a way of getting points in the tiers. This one is for ventilation system, service hot water. This is the interesting one. And I'm going to ask your indulgence for me to soapbox for just 1 minute. I dislike this with the fire intensity of 1,000 suns, and I'll explain why. So what this says is, if I decrease the volume of my building, I get energy conservation points for it. You're rewarding geometry. Show me another place in the code where I reward geometry. It doesn't exist. That's a really interesting thing for me, because, and I'll explain why I think this is important, and it will tie into the kind of exercise we'll ask you to finish the day with. If I have written a code that is geometrically agnostic, okay, doesn't tell me what shape the building should be, doesn't tell me, it just says here's the bits you need to consider. And indeed, if you use a performance model, I'm going to ask you to hold that geometry to be the same. To now say, oh, no, you should get points because you've made a smaller building. Yeah. I don't know if that's the right thing to do, because a code is a minimum standard I can write. I can wrap my head around that. Do this and you've met code. That's how many times have you used that phrase? This meets code, right? Now it's saying, here's a good design principle. If you're writing a code, you probably shouldn't be writing a best practices manual, because they're different. They're intrinsically different documents. Again, code is a floor, not a better way to do something. And that's kind of the reason this exercise is meaningful, because to me, the better way to do this is, how do you do this part? How do you incentivize people to realize a smaller building is more energy efficient and build that, as opposed to weirdly rewarding things in a very complex compliance path. I'm going to call up Hussein again. That's the end of the me talking part of this, but we're gonna ask you a couple questions to round out the day. So again, think about what you talked about this morning. How do you think about the legal context? Think about the idea of incentives. Think about where the energy flows in a building. And there's a couple questions, because now I hope we've given you enough knowledge to say, okay, we talked about incentives in the beginning of the day, broad stroke. But what do I do if I have to think about economics now? So now I'll give you a very simple example. I want to cut down the amount of thermal loss from the envelope. I can put in better windows, better walls. I can put in a better ceiling, or I can make a smaller building, or I can make the windows smaller. All five will literally do what I'm asking it to do. But as anybody who's ever priced a building out would know, they have vastly different implications. So, Hussein, there we are. Oh, sorry.
I do a program benefit the president at their project.
Yeah.
For the point is then you see that in anything. Correct.
Yeah. The short answer is no. Codes write codes for compliance. But you are absolutely correct. There would be nothing preventing you. As a matter of fact, let me half give you an answer to our discussion because your question is spot on. One of the ways you can do incentives is to actually say, let's take a point system, for instance. Just humor me for 2 minutes. We know there's a certain amount of points associated with the size of a building. If the city of Calgary put in an incentive that said, for every building volumetrically less than, 300 cubic meters or 10 points in the tiered system, we'll give you a $5,000 incentive. You can easily build programs based on all of these things. One of the good things I will say about the point system is it shows links that you would not normally intuitively make. So a lot of people would never think about, window performance separate from wall. But the points really does force you to think like that and how much better it has to be. So I guess the short answer would be, no, the point system was not designed to create incentives, but it is very easy to imagine an incentive system based on specific point allocations.
Can be at home.